challenge problem. All right. Okay, so for our challenge problem, we have a reaction vessel at 27 degrees Celsius that contains a mixture of SO2 with is a certain pressure and oxygen at a certain pressure. When we add a catalyst, we get this reaction to take place. Right? And then if we wait a while at equilibrium, we find that the total pressure is equal to 3.75. We want to then calculate this equilibrium constant in terms of the concentration. Right? So we're going to do a variety of steps here to calculate this. So if we look, we can define this equilibrium constant, capital K, and we're going to define it in terms of pressure. Right? That is going to be equal to, again, the pressure of the products raised to their coefficient divided by the pressure of the reactants raised to their coefficients. And eventually we want to calculate what this value is, because if we get this value, we can calculate Kc, right? Because Kc and Kp are related, and we have an equation for this, right? We have that Kp is equal to Kc times RT change in N. Right? So if we can calculate Kp, we can then calculate Kc. Well, if we look at this, the information that we have is about the start of this reaction. Right? So we can define this reaction at, again, I'm gonna write down the reaction again. It's an equilibrium with 2SO3 as a gas. Right? So we can define this reaction system, what it is initially. Right? And initially for our SO2, which I can't write, our initial concentration for SO2 was 3 atmospheres. Right? Our initial concentration or initial amount of oxygen is 1 atmosphere. Right? And we're assuming that this, because we didn't put any of this into our reaction vessel, we're going to assume that initially we have an amount of 0. The partial pressure of that gas is going to be 0. Right? And regardless of what this value is up here, right, whatever value that it's going to be a number that is greater than 0, right? Which means at equilibrium, we have to have some mass of, or some amount of the SO3. So we're going to shift some of this mass, and this reaction is going to move in that direction. Let's actually change the color of that arrow. Right? This is going to shift this way, which means that we're going to experience a change, is where this C comes in. Right? And our change is going to be that we're going to lose some of this, which means we're going to have to lose some of that, and we are going to have to form some of this. Right? So we're going to have a subtraction on the reactant side and an addition on the product side. Right? But we don't know necessarily how much is going to be lost or gained. So when we don't know how much, we usually use a variable, and that variable is X. Right? So if we look at this, if we make this amount X, right, we know that for every one of the oxygens that are lost, how many SO2s have to be lost? Right? For every one of these, we need to lose 2 of those, right? So if this is the smallest whole number amount we can lose, we're going to lose twice as much of that in terms of the SO2, right? Which means over here, because of this 2, we are going to gain twice as much as that. So these coefficients have to be carried down in front of our x's, because the x is our smallest whole number transfer right? If we think about it in terms of moles, right? So as we get to the end, or as we reach equilibrium, our pressure is now going to be 3 atmospheres minus the amount we lost, which would be 2x. The amount of O2 would be 1 minus x. And the amount of SO3 is going to be 0 plus 2x. Okay. Everybody, so this is what we refer to as an ice table. We're setting up the initial conditions, predicting which way we have to move to get back to this equilibrium, right? And we are going to then move that mass by either subtracting or adding, depending on what, right? And I will warn you, we can set up an ice table that we actually move in this direction, right? That is possible, in which case we would be subtracting here and adding there. This case, that's not, or in this example, that's not the case. So it doesn't always have to be subtracted from the reactant side and added to the product side. It depends on where we are in comparison to equilibrium. Right? That makes sense. All right. So now we have to find a way to solve for x, right? Typically, if we have this value, right, we could set up this expression, and that would allow us to solve for x. But now we don't have that value. So there has to be another way that we can solve for x, right? And that comes from this here. We can say that at equilibrium, the pressure of the SO2 plus the partial pressure of the O2 plus the partial pressure of SO3 has to equal the 3.75 atmospheres. This value here. Well, we don't know exactly what those pressures are at equilibrium, but we have a representation for those. So we can put these numbers in there. So this is going to be 3.0 minus 2x plus 1.00 minus x plus 2x. I'm going to ignore the 0. And all of that has to equal 3.75. Because of the rules of partial pressures. The sum of the partial pressures has to equal the total pressure of the system. So now we can solve for x, right? We're going to combine these, so it's going to be 3 plus 1, so 4.0, 2x minus x, which would be minus 3x plus 2x, so that's going to be a minus x is equal to 3.75, which means x, let's go the other way. I'm going to move the x in this direction, so it's going to be 0.25 is equal to x. Right? So with that, we can now plug those numbers into here. So our Kp is going to be equal to our partial pressure of SO3 at equilibrium, which was 2 times the 0.25, which would be then cubed, divided the partial pressure of SO2, which would be 3.0 minus 2 times 0.25, all squared. And this would be squared, not cubed. Times the partial pressure of oxygen, which would be 1.0 minus 0.25. So if we did that math, the top ends up being 2 times that is 0.5. 0.5 squared ends up being 0.25. The bottom ends up being 0.25 times 0.75, right? And this whole thing ends up equaling 0.0533. according to my math the other day. So now we calculated the equilibrium constant in terms of pressure, but the question wanted us to calculate the equilibrium constant in terms of concentration, right? We wanted this value here, right? So then we would say that, again, rearrange this equation. So Kc is equal to Kp over RT to the delta N, which would be equal to the 0.0533 divided by R, since this is a gas, 0.8206 times the temperature. We said it was 27 degrees, so 27 plus 273 is 300 K. Right? All that has to be raised to delta N. So we have to look at the change in moles of gas. So if we look in our balanced reaction, we end with 2 moles. We started with 3 moles. So this is going to be 2 minus 3. When we do that math, our Kc, capital Kc, is going to equal 1.31 value. So whenever we solve these equilibrium questions, the first thing we have to decide is, or we should think about, is what is our actual equilibrium expression. We then define where we are now. We compare where we are now to where we want to be in terms of equilibrium, and we set up the appropriate ice table. And then the major work is to solve for X, right? Once we solve for X, we can go on. I will caution you though, because it happens to me all the time. A lot of times you will end up solving for X, and it'll be a pain in the ass, excuse my vernacular, right? And you will feel some satisfaction getting to X, right? But X may or may not be the answer you're looking for in the problem. So when you get to X, pause, review what you're asked to find, and then go from there. Right? One other thing that you may have to do is, if we end up with a expression here, right, that ends up being squared, we might have to use the Pythagorean, or not the Pythagorean theorem, we might have to do the Pythagorean theorem. Is that right? The quadratic equation, excuse me, Pythagorean theorems for triangles, right? Which is that X could be equal to B squared minus, no, hold on. Now I can't remember.
Negative b plus or minus the square root of b squared minus 4ac all over 2a?
Yes, square root of b squared minus 4ac all over 2a. Thank you. I should have written it down because I would, in a moment, forgot it, right? Where x squared, ax squared plus bx plus c is equal to 0. Right? So if we put our equation in this form, these numbers then go down here, and we can solve for X that way. Right? So be aware you may get to do that equation if we end up with a squared term, if we know this value and we're solving for X. All right. I'm going to stop recording.